In this video, we're going to start learning about new unit, simple harmonic motion. This unit deals with things that are attached to either pendulum that is moving left, right, or to a spring where a mass is allowed to oscillate back and forth. In this first lesson, we're going to learn about period of oscillations, both the period of the pendulum and the period of the spring. In the first 2 minutes, we're going to go over all the equations that you need to know in this unit, and then we're going to practice using these equations on a few practice problems. So let's firstly start by examining what are our new equations. Firstly, we have the equation for the period of the spring. Period T is equal 2 pi times square root of mass that is attached to the spring divided by K, which is the spring constant, right? So pretty straightforward. All of these variables we have seen before. So essentially, not surprisingly, the period of the spring depends on the stiffness of the spring, K, and the mass that is being attached to it. Now, also another interesting equation here is the period of the pendulum. So it has a very similar format, right? But it depends on the length of the string and G, the gravitational constant. Interestingly, it does not depend on the mass, right? So it does not matter what mass you attach to a pendulum, the period will be the same. The only thing that really determines the period here is the length of the spring. Many of you who are taking physics in college or high school probably have had a laboratory on this where you had to figure out what does the period of the pendulum depend on. And what you have probably figured out in this class, right, is that by basically taking a bunch of data, you figured out that it really only depends on length. There's no dependence on mass. Great. Some other things that we should keep in mind are these following quantities here. So this omega right here is the angular frequency, right? This is the Greek letter, that's how you read it, omega, right? And we can, this F over here is frequency. And another interesting, like a very important part is that period is the opposite of frequency. So remember, period is basically the time it takes for you to come back to the same point. So for example, for a pendulum, it would be like go there and go back, right? Frequency, on the other hand, is how many times, right? If I'm standing over here, for example, and I'm counting how many times per second does this pendulum come to me? Like, for example, 5 times per second. So as you see, like the longer the period takes, the longer it takes for it to go down, the less counts per second I will have. So frequency and period are like the opposite quantities of each other. And then there is this quantity of angular frequency, right? Which you can calculate by multiplying normal frequency by 2 pi. Now, this we'll look over in more detail in another unit, right? But I just want you to keep in mind that if you have period, you can convert it to frequency or angular frequency. Great. So in this video, there's not going to be a method like we typically do because there's simply only one formula. So all of the problems that we'll have to deal with today will just be about manipulating and plugging stuff into these formulas. Starting with the first problem, where we have to find out what will happen to the period of the pendulum if I increase the length of the string by 4 times and 16 times. So let's firstly start with the equation for the period of the pendulum. So what I recommend you do is that you rewrite this equation and you write that pendulum is proportional. So this is a proportionality sign, right? It basically allows me to write down just the 2 variables that I want to analyze, right? Let's say if I keep everything else the same, right? Because 2 pi is a constant and G is a constant as well, period is related to the square root of length, right? Again, this sign means it's not exactly equal to, but it's related to square root of length. So I'm basically dropping all the other constants. Why should I write it like this? This way of writing it allows me to essentially directly plug in, right? If I'm saying that length changes by 4 times, so increases by 4, I can just plug in 4 for length and square root of 4 will be 2. So I can say that my period increases by 2 times. If let's say I increase my pendulum, right, if I increase the length of my string by 16, I can plug in the factor of 16 for length, and square root of 16 will be 4. Just like this, right? Amazing. So it's a really useful, this kind of like proportionality sign is a really useful quantity, right? Let's say, for example, if my length was decreased by 1/4, right? I would plug in 1/4 and my period would change by a factor of 1/2. So it kind of simplifies the algebraic calculation. So a lot of these questions could show up, for example, in multiple choice section of your exam. Right, now let's take a look at calculating period for the spring. So in this example, we have a mass of 0.5 kilograms attached to a spring and set into oscillation. The mass completes 20 oscillations in 40 seconds. Find the period of one oscillation and determine the spring constant K of the spring. So what does this really tell us here? 20 oscillations in 40 seconds. So this indirectly gives us the information for the period of the spring, right? The period is the time for one oscillation. So to get the time for one oscillation, we need to take 40 seconds and divide it by 20 oscillations. So we get a unit of 40 over 20, so we get 2 seconds. If you're ever not sure, like for example, like you're given this information, but you're not sure whether to divide 20 by 40 or 40 by 20, you can think about the units, right? The unit of period has to be in seconds. So seconds should be on the top and oscillations should be on the bottom, right? Because at the end, you want to get oscillations. Right, now that we know the period and we know the mass, we can take our equation for the period of the spring, which is 2 pi square root of mk, and the only thing that is really left is to just rearrange it for k. So let's practice rearranging this equation. Let's divide both sides by 2 pi. In order to cancel out the square root, you want to square both sides. So on the right hand side, m over k, the square root cancels out. Here, I can apply the square to each of these individual variables. So t squared over 2 squared is 4, and pi squared is, I just leave it as pi squared. Now, I want to get k, so what I can do is I can just inverse both sides. So 4 pi squared over t squared, I inverse left side, and I inverse right side, k over m. So I'm looking for k, so I can multiply both sides by m. And finally, on the right-hand side, the only thing I have is k, the spring constant. So let me plug in all the variables and just get a numerical answer. M is 0.5. Period is, we got 2 seconds, so 2. So k should be 4.93 newtons per meter as our final answer. Here you go. So now in the next problem, we're just going to do one more problem for this unit. We're going to solve here. We're going to adventure on a space exploration. So an astronaut on an unknown planet wants to determine the gravitational acceleration g on the surface of this planet to help to plan future activities. To do this, astronaut conducts a simple pendulum using a string and a small weight. The length of the spring is measured to be 2.5 meters. After setting the pendulum in motion, the astronaut measures the time it takes for the pendulum to complete 20 oscillations in 60 seconds. So just like before, right, we can, if we know 20 oscillations in 60 seconds, we can find the period. Given the length, right, is 2.5, find the gravitational acceleration. So g, right, g is no longer going to be 9.8 because we're on a different planet. So that's what we need to find. Now, just like before, we can find the period from the number of oscillations and the seconds, right? I want you to think, is it 60 divided by 20 or 20 divided by 60? Hopefully you said 60 seconds divided by 20. because we get 3 seconds per oscillation, right? So that's how long it takes for one oscillation to occur. So we have T, we have L, we just have to find G. Here's our equation for period of a pendulum. And just like in the previous problem, we just have to rearrange it, but this time for G. So divide both sides by 2 pi. By the way, you can stop this video and you can try to practice rearranging this equation on your own. Doing this on your own is always better because it's a better way to remember. But if not, and if you're confused how to rearrange it, of course, keep watching. So now that we have this, right, we're going to square both sides to cancel out the square root. Perfect. So again, I'm applying the square, right, to each of those. T squared, 2 squared is 4, and pi squared. So L over G. Now again, since I'm trying to get just G alone on both sides, now I could cross multiply it here, or I find it simpler to just inverse both sides. So 4 pi over squared, flip the left hand side and flip the right hand side. Finally, I will just multiply the left hand side by L to find my final equation for G. Let's just plug in all the quantities that we know. The length is 2.5 times 4 pi squared divided by T squared, and we have our final answer for G as 10.97 meters per second squared if you plug this into your calculator. Just like this. All right. So in the next video, we're going to find out how to find the period and how to find very important quantities from a graphical representation, right? The problems that we'll look over in the next video are very common in lab questions and very common on free response sections. So make sure you guys watch that. In the meantime, keep practicing these problems and keep watching these videos on your way to an A. Thank you guys for watching.